Good afternoon, folks. Happy Tuesday. Hope you had a good weekend. I actually got your exams graded, so they turned out much better than the first round of exams. So good job on that, on the whole. Anyway, so wait a second. I'm just thinking. Let me just get my tablet set up here. There we go. Well, hopefully you didn't think very much about math over the weekend. But does anyone have any questions? Okay. So did it seem like you had enough time? Sorry, go ahead. Sorry, I couldn't hear you.
I have a question.
What's your question?
When you have two matrices with the same polynomial, one of them is not diagonalizable. What does it mean?
So what I heard is something like if you have two matrices with the same polynomial, and then I lost you.
Yes. Okay, so one of them is diagonalizable and one is not. What does it mean? I mean, they're similar because they have the same polynomial.
Yeah.
But one is not diagonalizable.
So yeah, that can. It just means that, in fact, I think we might have even done we might not have done an example, but it just means that the same polynomial just means they have the same eigenvalues, but it's not saying anything about eigenspaces. So even though the matrices could have the same eigenvalues, the eigenspaces could be different. And if some of the eigenspaces are too small, so if their dimension is less than the multiplicity, then it's not going to be diagonalizable. So that definitely.
They're similar, right?
No, they're not necessarily. So the result is if they're similar, they have the same polynomial.
Yes.
But it's not the reverse. So if they have the same polynomial, that doesn't necessarily mean they're similar.
Okay.
I can so a quick example, let me see if I can come up with a quick example. So I'm just thinking, so of what you're saying. So this is an example of matrices with the same eigenvalues, same polynomial, characteristic polynomial. One is diagonalizable. The other isn't. Okay, and I'm just going to go for 2 by 2s and hope I get it right. So like if I have 3, 1, 0, 3, and then just the diagonal matrix, 3, 0. So in both of these cases, right, the characteristic polynomial is, is the determinant of 3 minus lambda, 1, 0, 3 minus lambda, which is 3 minus lambda squared. And that's equal to the determinant of 3 minus lambda, 0, 0, 3 minus lambda, right? But clearly, this second one is diagonalizable because it already is diagonal, right? But the first one is not diagonalizable because the null space is just one-dimensional. So the eigenspace, let me calculate the eigenspace in each case, right? Is equal to the null space of A minus 3 I. So that gives, in the one case, I'm working with this matrix, right? And so y has to equal 0 in order to make this true, right? So
can you share the screen?
Sorry?
Can you share the screen? Let's see.
Oh, I see, it froze. Yeah, hang on a sec. Let me just see if, yeah, it's definitely froze. Okay, so let me pause the share and resume the share and see what happens. Brother, there we go. Okay. So in the one case, the null space, so this, the first row here tells me that y has to equal 0. So, and x is your, oh, for goodness sake. How did I get that dot there? Anyway. The first row tells you that y has to equal 0, so your null space is spanned by x equals, or sorry, the eigenspace. Let me just say it. Eigenspace is the span of just 1, 0. But in the other case, when you subtract 3 from the diagonal, you get the 0 matrix. And what vectors are there? Now you multiply that times any vector and you'll get the 0 vector. So in that case, the eigenspace is all of R2. And there's just a sort of quick example of how, even though they have the same characteristic polynomial, so they have the same eigenvalues with exactly the same multiplicities, that's not telling us enough to say whether or not the two matrices are similar. So these are not similar matrices.
But didn't we talk about the theorem? The theorem that said they have the same polynomial, they're similar.
So the theorem that we said, that we talked about, is if A and B are similar, then they have the same characteristic polynomial. Right? That's a different thing from if they have the same characteristic polynomial, then they're similar. So right now you're asking a different question because you're saying, hey, if they have the same characteristic polynomial, does that mean they're similar?
So you first assume they're similar.
Yeah.
Answer the second question.
In this theorem, which is true, right? This is still a theorem, okay? In this theorem, you're starting by assuming that they're similar. So you have this P inverse AP that equals B, right? Here, you're starting by assuming they have the same characteristic polynomial, which is this part. And that does not imply that they're similar. So, however, there are matrices with the same characteristic polynomial that are not similar. And this, see above, right? And that does not contradict this theorem, because this theorem starts by saying, hey, let's start with similar matrices. Well, these aren't similar, so I can't even apply this theorem.
Well, if I give you two matrices, arbitrary matrices, and ask you, are they similar? I mean, how do you go about that? Because they might not be similar, they might be similar. And
yeah,
the one doesn't answer that.
So
it doesn't answer how you prove or verify that they're similar.
So that in general is not an easy question to answer.
Okay.
It's probably easier to say they're not similar than it is to say they are similar in general. But we do know that, using eigenvectors, you can determine when one matrix is similar to a diagonal matrix, for example. But I wouldn't, like, I'm not going to give you two matrices and say, hey, are these similar? Unless you can really tell me that they're not similar.
Okay. If I have to figure out the similar, what would I do? I mean, maybe maybe this class is not about that. Maybe what would you do?
So I would start like you did by looking for contradictions, right? By seeing, like, you can easily see, well, not easily. Yeah, I mean, easily. You can have a computer see if they're diagonalizable, right? And if they're diagonalizable to the same diagonal matrix, or one with the same values, on the diagonal with the same multiplicities, then they would be similar. So
Okay.
the problem with this example is they're not both diagonalizable. If both of these were diagonalizable, then they would be similar.
Okay.
But the non-diagonalizable ones are a much harder question to answer. Like I don't even know how to answer that question. I'm sure somebody does, but I don't know how to answer that question.
Maybe the computer.
Yeah.
Okay, thank you.
You're welcome. Other questions? Okay. So let me go ahead and why is that up there? Let me go ahead and remind us where we were. Okay, so it's been a while. You guys have been worried about the test. You got the test taken care of. And we've forgotten, I mean, thank you, Hector, for asking about 5.1 through 5.3. I just want to reiterate or remind you that I'm done lecturing on those sections. Okay, so we've covered 5.1 through 5.3. And you should be catching up on the work from there if you aren't already. And what I'd like to do today is talk about one context where this idea of similarity can be useful. So how similarity can be useful in the context of linear transformations, okay? And that's section 5.4. So this is eigenvectors and linear transformations. And it's going to take a little bit to kind of combine the two, to connect the two. Okay, so a little bit of review. Recall when we had a linear transformation. Oh, I should also mention, if you start reading section 5, actually, I should give you the homework, right? So the homework from 5.4 is going to be 11 to 21 all. Now, section 5.4 assumes that you've done chapter 4, and we haven't talked about abstract vector spaces. So when you start reading section 5.4, there's going to be a lot of stuff that doesn't make sense. So you can basically skip that, okay? So there's no, oh, yeah. So there's no, I'm not assuming that you're going to understand stuff on general vector spaces or anything like that. So you can ignore that stuff. I'm just going to do it in the context of linear transformations on our Rn. Okay. And so let's recall that, right? So let T mapping Rn to Rn be a linear transformation. Actually, recall what that means. A linear transformation means that T of x plus y is equal to T of x plus T of y. And it also, the other second property was T of C times x was C times T of x. Okay. So if we start with a linear transformation, and actually, what's your favorite linear transformation? Actually, what's an example of a linear transformation?
Reflection on the x-axis.
Reflection on the x-axis. That works. What's another one? I know I'm pushing my luck here. I should just take it and go, right? Yes, so reflection on the x-axis. In fact, reflection across any line through the origin works, is a linear transformation. If the line does not go through the origin, reflecting across it is not a linear transformation. Rotations about the origin are linear transformations. Rotations about other points are not linear transformations.
Dilation also?
Dilations from the origin are linear transformations. What about translations?
You need the, how do you call the,
Homogeneous.
yes.
Yeah,
Yes.
the homogeneous coordinates. That's right. So just in the plane, a translation is not a linear transformation. Okay. When you have a concept like linear transformations, it's good to just have examples of things that are and things that aren't linear transformations. Okay. What we saw way back in the day was that if you give me any linear transformation, I can find a standard matrix so that that linear transformation is just matrix multiplication, right? So let that be a linear transformation, then the matrix, the standard, let me write that, the standard matrix A for T is the one whose columns are the images of the standard basis vectors. E1 through En, right? And remember, those standard basis vectors are the ones that have a 1 in the ith slot and a 0 everywhere else. Okay. So another way to say this is A is the matrix whose first column is T of E1, second column is T of E2, and the last column is T of En. And we saw, so it's a fact that if you know A, that then the linear transformation on any vector X is just A times X. Okay, so this is a big deal. And we talked about this a while back, so it might be a little bit rusty, right? But what it says is if you know exactly where the standard basis vectors go, you essentially know a formula for finding where any vector goes, right? For a linear transformation. So for example, find the standard basis, standard matrix, my bad, for 90-degree rotation counterclockwise. So I have CCW as my counterclockwise rotation about the origin. So let me remind you how that goes, right? So I'm going to consider this transformation, and I just have to know what happens on the standard basis vectors. So I have, excuse me. Oh my goodness, my allergies are kicking up. Okay, I have E1 and E2, and I can apply the transformation to them. So that's just rotation by 90 degrees. That means pointing to the right horizontally ends up pointing up vertically. Pointing to up vertically ends up pointing to the left. And so these this image, this T, of E1 is just 0, 1. Pop quiz, what is T of E2 in coordinates? Well, it points the opposite direction as E1. So it's going to be -1, 0. And that tells us that the matrix A is equal to, the first column is 0, 1, because that's the image of E1. And the second column is -1, 0, because that's the image of E2. So that's knowing exactly where two vectors go, right? I know where E1 goes and I know where E2 goes. And now the result tells me that to find out where any other vector goes, I just multiply it by this matrix and I get where it goes. Okay. So what I'd like to do is verify this fact. Okay, this is a nice fact, nice observation, right? That if you use this particular matrix, this matrix whose columns are the images of your standard basis vectors, then the linear transformation on any vector is equal to that matrix times the vector. So I'd like to verify this fact. That T of X is equal to A times X. Okay. And first, so step one, and I'm just going to do it for the two-dimensional case. So suppose I have X is just equal to the vector X1, X2. Well, I can think of that as the vector X1, 0 plus the vector 0, X2. And now I can factor the scalars out, right? So I can take this X1 and I can pull it out, take the X2 and pull it out, right? So this equals X1 times 1, 0 plus X2 times 0, 1. And now using this sort of simplified notation, this is X1 times E1 plus X2 times E2. So what I've done is I've written my vector X as a linear combination of the standard basis vectors. So step one is write X as a linear combination of, maybe I'll even put this in blue, write X, the general vector X as a linear combo of E1 and E2. And then step two is use the linearity of T. Okay, so let me describe what I mean by that. Okay. So I'm trying to verify that T of X is equal to AX everywhere. And remember, the only place I knew was on E1 and E2, right? So that's really the only place I know. Okay. Also, I guess it would be good to remember that linearity means it distributes across sums and you can factor out scalars, right? That's what T being linear means, you can do that. Okay. So now I want to start with T of X and I want to do some calculations, okay, where X is this general vector X. I want to do some calculations here, and I want to end with A times X, where A is the matrix whose first column is T of E1 and second column is T of E2. Maybe I should even have that. A is the matrix whose first column is T of E1 and second column is T of E2. Oops, I don't know what that is. Okay. So T of X is equal to T of the vector X1, X2. Because that's what X is. Now, from step one, you know that I can write X1, X2 as a linear combination of the standard basis vectors. So it's X1, E1 plus X2, E2. This is by step one. And now is where the linearity comes in. Okay, so remember that the X's, the X1 and the X2, those are scalars. The E1 and the E2, those are just my vectors, right? My standard basis vectors. So according to this, I can distribute my T across the sum and then factor the scalars out. So if I do that, I'm going to get X1 times T of E1 plus X2 times T of E2. I get that linear combination. So this is bilinearity of T. Or let me just say, because T is linear. And this is what math people do a lot, okay? They talk about properties of something, and they use the properties rather than doing actual calculations, right? But this is just a linear combination of two vectors with weights x1 and x2. And remember, that's just a matrix times a vector, because a matrix times a vector is the linear combination of the columns of the matrix with the weights being the entries in the vector. So this equals, by definition, the matrix T of E1 is my first column, T of E2 is my second column, times the vector x1, x2. That's literally the definition of a matrix vector multiplication, if you go way back to chapter 1. But now, this matrix, whose columns are the images of the standard basis vectors, is just A. And this vector, x1, x2, well, that's just X. Okay. So I'm just trying to really hype the advantage of the standard matrix of a linear transformation. All you need to know is what it does, what the linear transformation does to a basis. Once you know that, you can derive a formula for what it does to every vector in, so for example, rotate the vector -3, 4, 90 degrees, and you get T of X equals, I just take that matrix 0, 1, -1, 0. I multiply it by -3, 4, and I get -4, -3. And that's it. Done. Okay. Any questions about that?
So that is for matrices in the 2 by 2. So that.
Sorry, I lost you again. Could you repeat the question?
Only applicable for a matrix that is 2 by 2.
Oh, this works for any dimension. I just didn't want to write it all out, right? Because I could have n variables here and then have 1, 0, 0, 0, 1, 0, 0, 0. Yeah, so this is for n dimensional. I just didn't want to write it out. Yeah. Other questions or comments? Okay, so that's one thing. Another thing is we've seen that a vector space can have lots of different bases, okay? So I want to recall that. So our ultimate goal is to talk about similarity and to see how similarity is related to, can be used in linear transformations. In order to do that, I got to remind you about other bases. So let's recall that if script B equaling, vectors B1 to Bn is a basis for Rn, and X is any vector in Rn, we can compute the B coordinate vector, can compute the B coordinate vector, which is this bracket X with a subscript script B, right? Okay, and let me just give you an example to remind you. So let script B equal the two vectors 1, 1 and 1, 0. This then script B is a basis for R2. Okay, so my question for you is, what is a basis? What properties does this set have to have for it to be a basis for R2? Linearly independent and spanning, right? It has to have both those properties, linearly independent and spanning. Well, at the end of the section on bases, there was a theorem that said, if my collection has the same number of, if the number of vectors in my collection equals the dimension of my space, then one of those two properties implies the other. Meaning, if they're linearly independent, they also span. It also means if they span, then they're also linearly independent. Okay. So there's this result that says if this collection of vectors has the same number of vectors as the dimension of the space and one of the two properties, then it also has the other. So in this case, well, let me just write, because the vectors, they're linearly independent, or because any two linearly independent vectors in R2 form a basis. This is like some theorem at the end of section 2.9. It has to do with dimension. The basis theorem, theorem 15 in 2.9. Okay. So that thing's a basis for, oh, by the way, how do you know that they're linearly independent? Using the fact that there's only two vectors, how could two vectors be linearly dependent?
Are multiples of each other?
Yeah, only if they're scalar multiples. And these are not scalar multiples of each other, right? So clearly they're linearly independent. Okay. Okay, so that's a basis. I can ask to find the B vector for x equaling, let's say, 3, -4. And I want you to recall that the B vector for this guy is going to be C1, C2, where the vector x is equal to C1 times the first basis vector plus C2 times the second basis vector. This, by the way, is the definition. Okay, what is the B vector? It's the vector of weights when I write x as a linear combination of my basis vectors. Okay, so in order to do this, I just got to solve, in order to find the B vector, I just got to solve this equation where x is 3, -4. Okay. So I got to solve. Three -4 equals, sorry about that, C1 times 1, 1 plus C2 times 1, 0. And I'm going to show you like a way that we haven't talked about it before, called a change of coordinates. Just because it'll be convenient to be able to do this efficiently and quickly. Okay. So if I want to solve this, the right-hand side is just the product of the matrix 1, 1, 1, 0 and the vector C1, C2, right? Remember, the definition of a matrix times a vector is it's the linear combination of the columns where the entries in your vector are the weights. So this up here is the definition of that matrix times the vector C1, C2. Now, if we call this, we can find that in, so we want to solve this equation for C1, C2, and this is a matrix equation. One way to solve this is to left multiply by the inverse. So to solve, can left multiply by the inverse of this matrix. And that's a 2 by 2 matrix. And so 2 by 2 matrices, we know how to calculate the inverse of it, right? We know how to calculate the inverse. It's going to be 1 over the determinant times the matrix you get by swapping the diagonal entries. So the 0 in the lower right moves to the upper left, and the 1 in the upper left moves to the lower right. And then negating the off diagonal entries. Now that's just a tricky formula that works for 2 by 2 matrices. So you don't want to generalize that. I mean, we didn't go over it, but there's ways you can do it using determinants and stuff. Okay. Now, in this example, what's the determinant of my matrix 1, 1, 1, 0? What's the determinant of this guy? It's the product of the diagonals minus the product of the off diagonals. So that's 0,
1.
-1, right? Because it's 0 minus 1. So this determinant I'm going to erase, and it'll be, and replace it with -1. So I'm going to left multiply this equation by that matrix, and I'm going to multiply through by -1, right? So those will be positive, the lower right will be negative. Okay, so what you get is 0, 1, 1, -1 times the vector 3, -4 equals 1, 1, 1, 0. Oh, sorry. Bad. 0, 1, 1, -1 times 1, 1, 1, 0 times C2, C1, C2. And you don't have to write them out. Oh, shoot, I should have put some more room in there. But you don't have to write these out, because what should this be? What should this product be of these two matrices? This matrix times that matrix, what should it be? Well, the first matrix is the inverse of the second. So what should that be? What's P inverse times P?
The identity?
That's just the identity matrix. And you can verify, like if I take this first column and multiply it by this matrix, I'm going to get 1, 0. So in the product, the first column will just be 1, 0. The second column is multiplying by 1, 0, and I'll get 0, 1. So this product will be the 2 by 2 identity matrix. And that's by design, right? I wanted to get this matrix out of here, so I multiply on the left by its inverse, and then it goes away. And we know that the identity times anything is just the anything. It's whatever you started with. So that product is just C1, C2. And this is going to be -4, 7. So notice we just calculated the B coordinate vector of X, right? So our original X was 3, -4. We knew that if we found the vector C1, C2, that would be our B coordinate vector. And what we just did is we found that C1, C2 is -4, 7. So that means the B coordinate vector of this guy is -4, 7.
That was a test question, right? Remember the last test?
Similar to this, but this is slightly different. Because on the test, you had a 2-dimensional subspace of 3 space. And here, the difference between that and this is just 2 different bases for all of R2, right? So these are 2 vectors in R2.
Okay.
And the reason I point that out is because I'm going to sort of generalize this trick as long as it's a basis, a non-standard basis for all of Rn, but not for subspaces. So I'm going to describe how to find this B coordinate vector when it's a non-standard basis for Rn. But it wouldn't have worked on the exam question. Okay, so notice that this matrix right here just comes from the 2 vectors, 1, 1, and 1, 0, right? The columns of the matrix are 1, 1, and 1, 0, and those just come from my original basis, right? So if you oh, wait, went the wrong way. So I can think of if P, let me do this in a different color. Suppose P is equal to the matrix whose columns are the vectors in B. Then this is my P. And this is my general vector X. And that's equal to now remember that the C1, C2 is my B vector for X, which is what we're looking for, right? So the C1, C2 here, I can think of that as my B vector for X. Okay, so what that means and what this calculation shows you, since B is a basis, you know that the column and which form the columns of P, you know that the columns of P are linearly independent because basis vectors are linearly independent. It's a linearly independent spanning set. So you know the columns of P are linearly independent. Well, if they're linearly independent, then P is invertible. And I want to solve this. I know X, this is what X is. And I want to find the B coordinate vector for X. So I can solve this, and I know P because I know what the basis is. So my X and my P are the knowns. The unknown is the B coordinate vector for X. Since the columns of P are independent, this is invertible. So I can left multiply here. It's going to be P inverse in general, right? So this will be P inverse times X. This will be P inverse times P times the B coordinate vector, which of course is just the B coordinate vector. So in general, what you see is that the B coordinate vector is just P inverse times X. And this is where B is a basis for Rn. So this does not work on subspaces like the question on the exam, where B is a basis, because in the question on the exam, it wasn't even a square matrix, right? It was 2, 3 vectors. And so when you make this matrix, it's not going to be invertible. Anyway, so there are some restrictions. P is a basis for Rn, and B is a basis for Rn, and P is the matrix whose columns are your basis vectors. And this is true for any X. Okay, so this is true for any X. Any questions about that?
So this is chapter Professor Roland, right? Or your name?
Yeah.
This is a chapter, well, what chapter is this?
So this is way back in when we were talking about bases. I mean, I'm just showing you a new way to calculate these vectors. So
2.3, I guess.
Yeah, 2 point something. Subspaces. Yeah, maybe 2.3. Okay. Let me remind you what we're doing here. I want to remember algebraically what's going on here. So what we're doing in this context, the negative, we're writing my original vector 3, -4 as a linear combination of 1, 1, and 1, 0. Okay. So I'd like to change the share to, and I want to go to GeoGebra. Oh my goodness, what's going on? GeoGebra. So, and you should too, okay? You should too. So let me just do this. Okay. And once you get to GeoGebra, I like GeoGebra Classic. Okay. So why can't and what we're going to do is we're going to look at the vector tool. So up in this line tool, you have all these tools up in the toolbar. Choose the line tool and go down to vector. All I'm trying to do is give you a visual. So we've talked about sort of an algebraic way of writing one vector as a linear combination of the other. The vector, oh, and when you have this vector tool chosen here, you just click on its initial point that starts it, and then its terminal point. So I wanted to go 3, -4, that goes here. That's my vector x, 3, -4. My basis vectors, the first basis vector is the vector 1, 1, so that it calls it v. And the second basis vector is the vector 1, 0. So I just click on the origin, then go out to 1, 0. And my whole goal is to write B as a linear combination of V and W. What we found was that the B coordinate vector was -4, 7. What that means is if it's -4 times my vector V, which is going to go the opposite direction 4 times as long. And then it's set plus 7 times the vector W. Since we're adding vectors, we do it tip to tail. So I'm going to start it at the end at this point E, and then go 7 times as long as my vector W. And when I do, I get back to the end of my original vector U. What this is supposed to demonstrate is that -4, 7 tells me I need -4 V's plus 7 W's in order to get to that point B, the end point of U, right? So that U, my original vector, is -4 times V plus 7 times W. Any questions about that? About the geometry or GeoGebra in general? Okay, well, we probably need a 5-minute break here, so why don't we reconvene at 10 after, and we'll keep going. So I'm going to stop the share. Sorry, I'm late. Okay, so what we want to do this half of class is put the two ideas together that we just talked about. You'd think I could finish chewing before coming up and talking, but no. Okay, so the two ideas were that of a standard matrix. So this fact, the standard matrix for A is the one whose columns are the images of the standard basis vectors, and that vectors can be represented in terms of different bases. So those are the two ideas we want to put together. So we're going to talk about the B matrix of a linear transformation. Okay, so let me give you a definition. Let script B equaling, say, the vectors B1 through Bn be a matrix, sorry, be a basis for Rn, and T mapping Rn to Rn, a linear transformation. The B matrix, which its notation is just like, looks like a matrix with a T in it and then a subscript B. The B matrix for T is the one whose columns are the B vectors of the T of the BIs, okay? So so basically you do something very similar to the standard matrix. For the standard matrix, the columns were the images of the standard basis vectors. For the B matrix, the columns of the B matrix are the images of the B basis vectors. But the only thing is you need to write them in terms of the B vectors. So notationally, it gets a bit cumbersome because it's saying take the images, take the image of B1 and find its B vector. Put that in the first column. Take the image of B2 and then find its B vector. Put that in the second column. And then the image of Bn and find its B vector and put that in the nth column. And make that T. That's your B matrix for the linear transformation T. And let me just highlight this, compare with the standard matrix. Right, where A is just the matrix whose columns are the images of the standard basis vectors. So these are very similar, right? The B matrix and the A matrix are very similar. Basically, you apply your linear transformation to your basis and then put them in as columns. The only added feature with the B matrix is you have to take the B vector, not just the vector of the image, not just the image, right? So you take the B vector of the image, whereas down here, you're just taking the image. And okay, that may seem like a difference, but it turns out that the standard basis vector is the standard basis vector. So they really have more in common than you might think. Let me do an example because that's a lot of letters. But again, the idea is find the images of your basis vectors, then find their coordinates, their B coordinates, and put them into a matrix. Okay, so let's just do that. So example, let script B equal the matrix 1, 1, 1, 0, right? And I want to find, and T be, so find the B matrix. Of the 90-degree counterclockwise rotation. Okay. So let me write it out as step 1 is just find T of B1 and B2. So again, this is just 90-degree rotation, only now we're using different basis vectors. So I want to know where 1, 1, so B1 is the vector 1, 1. If I, so that, you know, splits this quadrant in two, right? It's a 45-degree angle on both sides. So if I rotate that 90 degrees, it's going to split that quadrant in two and give me T of B1. Well, what are the coordinates, the standard coordinates for that going to be? If it's 1, 1 here and you rotate it 90 degrees, it'll be negative 1, 1. Because it doesn't change the length, right? It just changes the direction. And then B2 was the vector 1, 0. And if I rotate that 90 degrees, I get T of B2. Then the thing that was horizontal rotates and becomes vertical. So that's equal to 0, 1. Okay, so you found the images of the basis, the B basis vectors, right? So you take your B basis vectors, you find their images. And then so we know what the images are. Now we have to find their B vectors, okay? But let's remember that the B vectors are just going to be P inverse times the vectors themselves. So these vectors are going to be P inverse times the vectors we just found. So step 2, you want this P inverse of T of B1, P inverse of T of B2. Where remember, now you won't have to do this in general, but remember what we're looking at here is the matrix P is the matrix whose columns are your basis, your non-standard basis. And we found P inverse from that to be 0, 1, 1, negative 1. So that tells me that the B basis vector the B coordinate vector for T of B1 should be this 0, 1, 1, negative 1 times T of B1. But up here, we just found T of B1 was this red vector, which was negative 1, 1. So that is a 1 and negative 2. And then T of B2 is going to be this P inverse 0, 1, 1, negative 1 times T of B2, which we found was 0, 1 up here with the blue vector. So times 0, 1, which is 1, negative 1. And so the matrix, the B matrix for T, these two vectors that we just found, the B vectors for the images of the basis, form the columns of the B matrix for T. So this is just going to be 1, negative 2, 1, negative 1. Okay. And any questions about that calculation? So it's very similar to the standard matrix, right? The standard matrix is the matrix whose columns are the images of the standard basis vectors. The B matrix is the matrix whose columns are the images of the B vectors, with the added feature that they have to be the B coordinates of those. Okay, and so here's the fact that makes this useful. So here's the fact, and that is, in terms of the B matrix, sorry, in terms of the B basis, you can use the B matrix just like you did the standard matrix. So the fact is that the B coordinates of the image of every vector is equal to the B matrix for T times the B coordinates of the vector X. So this fact compares with the fact way back at the beginning that said T of X equals AX for all X, right? Knowing where T sends the basis vectors tells us where it sends every vector. All you're doing now is you're just viewing everything from the B basis perspective, right? So so what this says is knowing how T acts on the basis determines its action on all of Rn.
One question here.
Mm-hmm.
Do we always need to draw the vectors?
No.
To find it?
No. I'm just doing it because it's helpful for me.
Okay.
But you can just figure out what a 90-degree rotation of this guy is, right? Algebraically, if you like. Okay. Any other questions about that? Okay, so I want to describe, so this was one way to calculate it, to sort of in detail. You find the images of the, each basis vector and then find their B coordinates and then make the matrix. Let me also give you another theorem or something. I don't think this is a theorem in the book, but or at least not stated this way. If A is the standard matrix for the linear transformation T, mapping Rn to Rn, and B equaling B1 to Bn is a basis for Rn, then the B matrix for T is just going to be P inverse AP, where P is the matrix whose columns are the basis vectors in B. Okay, and here's a quick proof of that. Not that, this. So here's a quick proof, which is not meant to, if I look at the ith column of P inverse AP, okay? What that's supposed to be is the ith column of the B matrix. Now the B matrix is the one whose columns are the B vectors for the images of the BI under T. Come on, you. So the ith column of this is P inverse A times the ith column of P, right? If I wanted to know the ith column of a product, I just take the ith column in the last matrix and multiply it times the matrix before it. So that's what this says. But now A of BI, right? A is the standard matrix for T. So this A times BI is just T at BI. So this is P inverse times T at BI. And that's because T of X equals AX for all X. But now we also know that the B vector is just of anything is you just left multiply by P inverse. So this is equal to the B vector of T of BI. Because in general, the B vector of X is P inverse times X. Okay. So I would like to do an application of this. Okay, this says if I know what my basis is, and I want to find the B matrix, I just have to conjugate the standard matrix by the matrix whose columns are the basis vectors. Okay. Okay, so let me just do an example that says define T of X equaling the matrix whose first row is 13, 24, second row is -8, -15 times X. So that means this guy is the standard matrix for T. Find a standard matrix, sorry, find a basis B for R2 so that the B matrix for T. So T sub B is diagonal. Okay, so let's see how we might be able to use the previous observation, the previous result. Okay, so in this previous result, we're told that if I let P be the matrix whose columns are the basis vectors, then the matrix P inverse AP is going to be my B matrix. So what I'm really asking for, I want to find a basis so that this matrix is diagonal. So I need a basis so that this matrix is diagonal. Well, that's the same as saying that P inverse AP has to be diagonal. So I'm just asking, so i.e. you need a basis. I need to diagonalize, the matrix A. If I can diagonalize A, then so if we can, we get that P inverse AP will be a diagonal matrix. That will be the B matrix for T, and the columns of P will equal B. Okay, so let's just go ahead and do that because we know how to do that. To diagonalize a matrix A, we have to find the eigenvalues and eigenspaces, right? And then the columns of P are just going to be the eigenvectors, the linearly independent eigenvectors of your matrix A. So this reduces to what we were talking about at the end of last week. Okay, so any questions about that before I proceed? All right, so let me remind you on how to diagonalize it. Step one is you want the eigenvalues. So I'm going to say that the determinant of 13 minus lambda, 24, -8, -15 minus lambda, that determinant has to equal 0. So this is 13 minus lambda times -15 minus lambda plus 8 times 24. I can't believe I didn't do this ahead of time. Okay, so let me see what 8 times 24 is. 192. So plus 192 equals 0. Okay, so I'm going to get a lambda squared, and then I'm going to get plus 15 lambda minus 13 lambda. So that's plus 2 lambda. And then 15 times 13 is 195. So this will be minus 195 plus 192. So that'll be minus 3 has to equal 0. And that factors into lambda plus 3 times lambda minus 1 has to equal 0. So my eigenvalues are 1 and -3, right? And that's something that we're reasonably comfortable with, reasonably familiar with at this stage. And now I find the eigenspaces, right? So step 2, eigenspaces. Okay. Let me just remind you, there's a theorem that it's diagonalizable if it factors into linear factors with distinct eigenvalues. So we know it's diagonalizable. To find the eigenspaces, I just take my matrix minus my eigenvalue, right? So for lambda equals 1, I'm going to take a minus I. So that's subtracting 1 from the diagonal entries, which would give me 12, 24, -8, -16. And that row reduces to 1, 2, 0, 0. Because the first and the second column is twice the first column. So the null space, so y is the, so you get x is minus 2y and y is equal to y. So the eigenvector is just going to be -2, 1. For lambda equals -3, I'm going to look at a plus 3i. I'm doing this relatively quickly just because we're toward the end of class, but you should feel free to stop me at any time if you have any questions. So if I add 3 to the diagonal entries, I'm going to get 16, 24, and -8, -12. So this is a little dicier. So this goes to 8 goes into 16 twice and into 24 3 times. And then similarly, the bottom two form the same ratio. So you'll get zeros down there. So really you just want 2x plus 3y to equal 0. Let me just tell you, like this works in 2 dimensions. This is a trick in 2 dimensions. This does not work in 3 dimensions. There's not an easy, there are ways to do this computationally. I mean, I could get fractions if I wanted to, but what I'm going to do is I'm going to swap the 2 and the 3 and then change the sign of 1. Swap the coefficients and change one sign, change the sign of 1. So I'm going to get a 3 and a 2, and maybe I'll make that -2. Because then I'll get 2 times 3 minus 3 times 2, which is definitely 0. Okay. Okay, and then step 3. Remember from all our eigenvalue stuff that P is the matrix whose columns are eigenvectors. So if P is equal to this, then I know that P inverse AP, I don't even have to do the calculations. This will be a diagonal matrix So it'll be a 2 by 2 diagonal matrix. So it'll have zeros off the diagonal. Does anyone remember what's on the diagonal?
1, -3.
The eigenvalues corresponding. So my first eigenvector, the -2, 1, had a 1, was corresponding to lambda equals 1. So you'll get the 1 there. And the second column of P, this eigenvector corresponded to lambda equals -3. So you'll get a -3 down there. Okay. And the last thing is we're going to use this fact, right? This theorem that says if the basis is the columns of this matrix P, then the B matrix is just the P inverse AP. So our original question said, find a basis for R2 so that that's diagonal. This matrix we just found is equal to the B matrix of the transformation, where B are just the columns, the eigenvectors. So B is just -2, 1, 3, -2. Any questions about that? I'm trying to think of how to describe this intuitively, right? Let me give it a shot. So maybe like an attempt at a geometric picture. Okay. So my original matrix was A, right? And that took, oh, let me remind myself and you what A was. Don't ask me where I got this big, ugly matrix. I definitely should have spent a little more time figuring out a nicer matrix, but.
Where did you get it?
Sorry?
Where did you get it?
I cheated. I started with the diagonal matrix. Can you guys see that? I can't see. I started with a diagonal matrix and I just conjugated until I got that matrix. So I knew I was going to get 1, -3 on the diagonal.
That's why.
Yeah, and I should have just looked at the numbers and said, let me do a different one. But in any case, that's where it came from. By the way, that's a good mathematical trick to work things backwards, right? In any case, E1 goes to 13, -8, right? So that's way down here, right? This is T of E1, and that's equal to the vector 13, -8. E2 goes to 24, -15. Oh my goodness, I can't even fit that in, right? So T of E2 is equal to 24 negative 15. And you can think of these two vectors as giving you a grid in the plane. And then these two vectors give you, and their images, the images of the grid just look like parallelograms that look like this. So if I have the line, oops, go ahead and get away. If I have the x-axis, which contains that one, that goes to that. And then the y-axis goes to this one. And you get this image of the grid over there. So that grid has been stretched and morphed and bent and flipped, right? Because the red vector goes below. So that's one way to try and visualize this using the basis E1 and E2. I definitely should have used. So now let's use a different basis. So let's use the vectors negative 2, 1. So negative 2, 1. And 3, negative 2. So that's going to be down here somewhere, right? This is 3, negative 2. If I want to know where those vectors go, I just use the B matrix. Okay, so my B matrix was much nicer. My B matrix, I believe, was 1, 0, 0, negative 3. Okay. And that means that negative 2, 1 stays where it's at. So this vector, negative 2, 1, maps under this matrix to itself. So that doesn't change because it's an eigenvector with that eigenvalue. Man, I'm really messing up with slopes because we're out of time. Okay, and the blue guy goes to negative 3 times itself. So I get this. And I really apologize because what should really happen here is you should get these parallel lines that make a parallelogram grid. And those actually stay the same because these two sides stay the same. They just stretch a little bit more. Okay, this guy stays the same and this guy just stretches up here. So the idea is it's easier to see geometrically if you consider, say, the image of this parallelogram. It's going to be the same shape. It's just stretched in one direction. It's stretched by a factor of 3 in this direction, and it's not stretched at all in the other direction. So the idea is that this transformation, which is given in standard coordinates like this, is much nicer if we look at it in terms of the B vectors than it was when we looked at it in terms of our regular rectangular grid. Because it was much more dramatic. It took this nice rectangular grid to a very strange, large parallelogram grid. it took this parallelogram grid to one that just stretched a little bit in one direction. And that's why it's nicer to think of them in terms of a diagonal transformation matrix. That's all. Okay. Any questions about that? All right, we're going to call it good. Have a great couple days, folks, and we will see you on Thursday.